From the dawn of humanity, people have gazed up at the night sky with a sense of wonder. The twinkling stars, the distant planets, the moon's soft glow, they all hint at a vast and mysterious universe beyond our world. We yearn to understand our place in this grand cosmic tapestry. How did our solar system, this collection of planets orbiting a single star, come to be? The quest to answer this fundamental question has driven astronomers for centuries. The search for answers takes us on a journey through history, from the ancient philosophers who believed Earth was the center of all creation, to the modern scientists who use powerful telescopes to study distant galaxies. Along the way, we encounter brilliant minds who dared to challenge the accepted view of the cosmos. Today, we have a remarkable understanding of our solar system's origins, thanks to centuries of observation and scientific inquiry. Billions of stars in our galaxy alone are likely orbited by their own families of planets. New discoveries constantly refine our understanding and raise new questions, reminding us that the universe is full of surprises. This essay will explore the fascinating theories about the formation of our solar system. For much of human history, the prevailing belief was that Earth was the center of the universe. This geocentric model, championed by ancient Greek philosophers like Aristotle and Ptolemy, placed Earth at the heart of a celestial sphere. The stars, planets, sun, and moon were all thought to be embedded in this sphere, revolving around our planet in perfect circles. The geocentric model was a powerful idea. It aligned with the everyday experience of seeing the sun rise in the east and set in the west. It also fit neatly with the philosophical and religious beliefs of the time, which often placed humans at the center of creation. The geocentric model's influence was profound, shaping astronomical thought for over 1,500 years. However, as astronomical observations became more precise, problems with the geocentric model began to emerge. The planets in particular posed a challenge. These retrograde motions were difficult to explain if all celestial bodies revolved around Earth in perfect circles. The 16th century ushered in a new era of scientific inquiry, and with it, a radical shift in our understanding of the solar system. In 1543, Nicolaus Copernicus, a Polish astronomer, published his groundbreaking work, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres. In it, he proposed a heliocentric model, placing the Sun, not Earth, at the center of the solar system. Copernicus's heliocentric model was not immediately embraced. It challenged deeply held beliefs and contradicted the teachings of the Catholic Church, which held considerable sway at the time. However, the elegance and explanatory power of the heliocentric model gradually won over many astronomers. One of the most ardent supporters of the heliocentric model was Galileo Galilei. Using the newly invented telescope, Galileo made groundbreaking observations that lent credence to Copernicus's ideas. He observed the phases of Venus, which could only be explained if Venus orbited the Sun, not Earth. He also discovered 4 moons orbiting Jupiter, demonstrating that not all celestial bodies revolved around Earth. Johannes Kepler, a German astronomer and contemporary of Galileo, made further refinements to the heliocentric model. Kepler's laws of planetary motion provided a more accurate description of planetary movements and further solidified the heliocentric model's place in scientific thought. With the Sun firmly established as the center of the solar system, astronomers turned their attention to a new question. How did this intricate system of planets, moons, and asteroids come to be? One of the earliest and most enduring theories is the nebula hypothesis, first proposed by Immanuel Swedenborg in 1734 and later developed independently by Immanuel Kant in 1755 and Pierre-Simon Laplace in 1796. The nebula hypothesis posits that the solar system formed from a giant rotating cloud of gas and dust, known as a solar nebula. This nebula, composed primarily of hydrogen and helium, the most abundant elements in the universe, along with trace amounts of heavier elements, began to collapse under its own gravity. As the nebula collapsed, it began to spin faster, much like a figure skater pulling their arms in during a spin. This increased rotation caused the nebula to flatten into a disk with a central bulge. The central bulge, where most of the mass concentrated, eventually became so hot and dense that nuclear fusion ignited, giving birth to our Sun. Meanwhile, in the cooler outer regions of the disk, dust and gas began to clump together. This process, known as accretion, started small, with microscopic particles sticking together electrostatically. Over time, These clumps grew larger, forming planetesimals, the building blocks of planets. The planetesimals, through collisions and gravitational interactions, continued to grow, eventually forming the planets we observe today. The nebula hypothesis provides a compelling explanation for many of the observed features of our solar system. While the nebula hypothesis is widely accepted, it's not the only theory out there. Over the years, astronomers have proposed various alternative theories to explain the formation of our solar system. One such theory is the capture theory, which suggests that the Sun captured passing planets and other celestial bodies with its gravitational pull. Another idea is the protoplanet hypothesis, which posits that small early planets or protoplanets collided and merged to form the larger planets we see today. This theory helps to explain the presence of moons and the diverse compositions of the planets. Despite their differences, all these theories share a common goal: to unravel the mysteries of our solar system's origins. As we delve deeper into the history of our solar system, we discover that the planets' orbits have not always been as stable as they appear today. In fact, the early solar system was a chaotic place, with planets migrating and shifting positions over time. One well-known event is the Late Heavy Bombardment, a period about 4 billion years ago when the inner planets were bombarded by a large number of asteroids and comets. This event is thought to have been caused by the migration of the giant planets, particularly Jupiter and Saturn, which disrupted the orbits of smaller bodies in the solar system. Beyond the known planets, astronomers are also searching for distant worlds that may exist in the outer reaches of our solar system. These shifting orbits and distant worlds remind us that our solar system is not a static place, but a dynamic and ever-changing environment. Our journey through the solar system's history has revealed a complex and fascinating story, but there is still so much more to discover. With each new mission and observation, we gain a deeper understanding of the processes that shaped our solar system. From the formation theories and shifting orbits to the search for distant worlds, the quest to understand our place in the cosmos continues. As we keep exploring, we not only learn more about our own solar system, but also gain insights into the countless other planetary systems that exist in our galaxy. The spirit of exploration drives us to push the boundaries of our knowledge and to seek answers to the fundamental questions about our origins and our future.